Okay, welcome everyone to our first HAI Weekly Research Seminar of the quarter. I'm Vanessa Parley and I'm the Interim Director of Research at HAI. I'm thrilled to join in conversation with Art Owen. Art is a professor of the Department of Statistics at Stanford, and his teaching focuses on applied statistics, including experimental design and Monte Carlo methods. He's best known for inventing empirical likelihood and for work on randomized quasi-Monte Carlo methods. Today, Art will speak about his research on the use of variable importance and the Cohort Shapley measure to explain black box algorithms. Variable importance measures have a long history, but the more recent interest in explainable AI is getting new attention. And this work is in collaboration with Masayoshi Mase, a visiting scholar from Hitachi, and Ben Saylor, a PhD student in statistics at Stanford. Before Art starts his presentation, a few logistical details. You can use the QR code on the screen to ask questions through Slido, or you can click on the link that will be shared in the chat shortly. I will be drawing from these questions after the presentation so that we can have a Q&A with Art. And with that, Art, thank you so much for joining us. We're very excited to have you. Feel free to share your screen.
Well, thank you, Vanessa. It's really great to be here to talk to HAI. And okay, so there's my screen. So I'm going to talk about variable importance, the Cohort Shapley method, and redlining. And opinions are mine. They're not Stanford's or Hitachi's or the NSF's. For those of you who know about Shapley value and variable importance, where we land, what we're doing is very close, almost exactly the same as conditional expectation Shapley. Our paper came out to archive around the same time as Najmi and Sundararajan. The difference is they don't like conditional expectation Shapley, and we do like conditional expectation Shapley. We're also very close to Lundberg and Lee's SHAP, except that we're excruciatingly fastidious about never using an unobserved data point. However, I'm not going to assume that you know about Shapley value, so I'll be explaining variable importance and Shapley value as we go. Well, lately there's a lot of progress in black box algorithms to make predictions. So neural networks, random forests, GlimNet, XGBoost, these can be very powerful. And these kind of methods, they'll find things that you wouldn't find by yourself. They might find things that you wouldn't get in a simple interpretable model like a linear model or a small tree. But we want it both ways. We want to be able to predict as well as something complicated, but we also want to understand as if it had been simple. So figuring out how to interpret or explain predictions is a pretty big problem. And also I'll look at fairness issues. Once you can explain variables, you can use that idea to address fairness issues. If a variable that shouldn't be important actually is important, whether somebody gets a loan, then that's a sign that maybe something's going wrong. Okay, but I'll start off with just, what do we really mean by importance of a variable? And so, we have this vector of predictors, x1 to xd, and which ones are important? Now, just saying what's important, that's not really explaining the model. It's not a complete story to explain the model, but it's an important first step. If you can say what's important, that gives you a clue as to what's going on in the model. My former advisee, Tao Jiang, and I had a paper on this some time ago, and we wrote about 3 different ways that something could be important. It might be important if it affects y in a causal manner. So if xj is causal, that's important. Or it might merely play an important part in your predictions. So it could be mechanically. If you want to be, a stickler, you could say, well, it's at least causal for y hat, even if it's not causal for the future y. So, and then the third way is, well, if we left it out, maybe we couldn't predict as well. So these are 3 different things that would make a predictor variable important? And they're all different. Usually this is the one that we kind of want scientifically, and these other ones might be the ones that we can get, but they're all three different ways that something can be important. And today, we're going to actually have a fourth way that a variable could be important. So there's a pretty big literature on variable importance. Indeed, there's several different literatures on variable importance. There's a very impressive survey by Wei, Liu, and Song in 2015. They tried to survey everything about variable importance in two literatures, statistics and uncertainty quantification. So uncertainty quantification is sort of a hybrid literature between statistics and applied math. And they looked at 197 papers. That actually included 24 survey papers. So there's a lot of work that's been going on in these other areas for quite some time. And then explainable AI kind of burst on the scene and got a lot of traction maybe 4 or 5 years ago, and which continues. Not that that was the first place where it came up. And this book by Molnar, the book is online, and so it's a guide for making black box models explainable. And there are a lot of other disciplines that are interested in an important being variable being important. For instance, economics cares a lot about it. The Shapley value has been adopted by these other areas. And law, insurance, fairness, they also all have to care about what makes a variable important. Well, so what does make a variable important? And we'll say that like the variable A, it's important if when you change A, that changes B, and B was important. Okay, so wait, how come B was important? Well, let's not go into, well, B changed C. Let's not go into an infinite regress or something circular. The idea is that you can transfer importance from something to something else, but we're not going to talk about creating importance. It's just you start with something that you think is important, and then you try to quantify what things change that, and then they become important. So we have, in our context, we have some black box function f of x, and x has d components, and the jth component belongs to some space. Maybe it's binary, maybe it's real, maybe it's a category. And then f is ordinarily a prediction of something else. It's like y hat of x. That's normally what we're looking at. And what we can do is, well, we can change x and see what happens to y hat. It turns out there's a combinatorially large number of ways to get that done. So like, what xj do you start with? Do you start with a default value, a typical value, any value? And like, what kind of changes do you make? You could make local changes. You could make global changes. You could change it just enough so that somebody gets the loan instead of getting turned down for the loan. So the size of the change, that's something you have to think about. And then while you're changing xj, what's going on with xk? Should that be changing along with it the way it might normally do, or should it be frozen and held fixed? Okay, now that we have computed many thousands of changes to y hat from changing x, how do you actually aggregate them? You take the sum, the mean, the median. There's lots and lots of choices, and you can never really enumerate them all. Even that paper with 197 references, that's not enough to enumerate all of the things that you might do. When we started getting into this, I realized that quantifying importance is actually harder than causal inference. So a lot of my colleagues and other people on campus, they are quite interested in causal inference. And I believe that measuring importance is actually harder to do than causal inference. And the reason is measuring importance is about the causes of effects, and it's not the effects of causes. And these kind of sound the same, but they're really quite different. And there's this nice paper by Holland in 1986, where he's essentially saying that statistical methods and experimentation and what we call A/B testing now, you can use that to look at the effect of a cause. And then he says, looking backwards to the cause of an effect It's just a much harder problem. I think he's kind of punting on that problem. And then he points back to John Stuart Mill, 1843, who also was talking about the difference between these two things. So one example is you might say, if I water the plant, then it's going to grow. And that's different than saying, well, the plant grew, must be because I watered it. Well, there could have been something else going on. There could have been, maybe it was actually the sunlight that made the difference, or maybe it was the fertilizer. And in the first case, you might actually have settings where the sunlight and the fertilizer vary, but the one thing that changes is watering versus not watering. So you can be a little bit more successful at finding this cause going forward. Looking backwards, it's pretty hard. And then also there are proximate causes and ultimate causes. If you're trying to get the causes of an effect, well, why did you fertilize it? Maybe it's because one of your friends said to do that, or the person in the store recommended this brand or that brand, or maybe the sunlight was there because it just wasn't that cloudy that day. So it gets a lot harder to measure variable importance than to do even causal inference. Causal inference is actually pretty hard already. Okay, so here are some examples in real life. There was a horrific plane accident in Tenerife, the worst one ever back in the 70s. And there were about 5 different things, like there was no ground radar, there was fog. There's another airport, but it was closed that day. There are 5 of these things. And you could well imagine that if any one of those had been different, the accident wouldn't have happened. Okay, so how do you apportion causality backwards to those 5 things? Or maybe some candidate won an election by 10,000 votes. Maybe it's not the candidate you wanted, so you're kind of disappointed. And there's some factor that actually moved. It moved more than 10,000 votes from the candidate you wanted to that candidate. Is that the cause? Maybe not. Like maybe something else moved 11,000 votes. How do you reason backwards? It's actually a lot harder. Okay, and then maybe your uncle got turned down for a loan because f of x was greater than 0. Why was f of x greater than 0? So usually in statistics, machine learning, AI, we can do holdout samples and bake-offs. So we could look maybe everybody could predict what's important and then see what happens in the future on a future data set. But a holdout data set isn't going to tell you why your uncle didn't get the loan. Everything about why your uncle didn't get that loan is baked into this function f of x. And you can't do a bake-off comparing 2 algorithms because you used only that one algorithm. And this f of x, it's completely known. It's 100% known. You can put any x's in that you want and leave out any x's that you don't want. So it's different from our usual thing. We can make a lot of progress by having what Donahoe calls a common task framework, where everybody tries to predict the same thing, and we see the accuracy go up, 80s to 90s to high 90s. That doesn't seem to be that available for us in variable importance methods. Okay, so what if D would be 1? So ultimately we care about relative importance, but you can sort of think about the absolute importance of a variable. And classical local sensitivity analysis just looks at a derivative. So that would be, we're going to make small changes around a default value. Now, if we average those small changes, then we get something, from maybe your calculus class, we learned about total variation. If you take the variance for random x, then you get something that people study intensely in global sensitivity analysis. And there are decades of papers and books on that. And that's actually the literature I came out of. And these can all be generalized to d greater than 1. Okay, so what does x actually do to y? Well, over here, we can look at the slope. So small changes in x do, modest changes here. Small changes in x don't do anything there. Over here, small changes in x always make a big difference, but large changes in x can hardly move the needle. Over here, small changes in x usually don't do anything. Every once in a while, though, it's a doozy. Okay, so these are all different ways that 1x could affect something, and then you have to keep score. How do you keep score? Well, it's got to depend on your goals and the scientific context. There won't be a one size fits all. Okay, and I mean, let's take a look at something pretty basic. If all you have is x1 plus x2, well, if x2 varies over a bigger range, it's got to be more important. It's easy to forget. You think of a function as being the formula, but it's also the domain that it acts on. But if you're multiplying, then I think this one's probably more important because it can get to 0. This one can't. So it's not just the formula, but it's the variable range that matters, and also the distribution in that range. And if x1 would be a deterministic invertible function of x2, that would change things too. So there's lots of subtleties and complexities that can come into this. Okay, so that was an admittedly slightly nerdy explanation of what's going to make something important. Then when it gets a bit more practical, there are two significant difficulties that I think everybody who handles data has to come to grips with and is probably already familiar with. First of all, there are interactions. If you're going to change x1, then the effect of that actually depends on the other variables. So that's an interaction. So if we're going to attribute importance to the variables, somehow two things that interact, we have to share them. We have to share the effect over the variables that participate in the interaction. The second thing that really complicates our life are dependencies. So if we're going to change x1, does that also change x2? Well, if this is your temperature in Celsius and that one is Fahrenheit, yeah, they better change together. Or if x2 is x1 squared. But if x1 and x2 are just correlated, what's really going on? And most of the methods that people use to quantify importance, they'll change some of the variables to hold the other ones constant. And that's a pretty natural thing to do, but it can get you into trouble. So here's some notation for this. We'll have a hybrid point. So there's 2 points here, x, and it has 9 components, and then there's z that has 9 components. And now let's take a subset of those variables. Okay, so it's variables 1, 3, 7, and 8. And we're going to take those out of variable z. And then the complementary set, well, just everybody that wasn't in 1, 3, 7, and 8. Okay, we're going to take those from x. So here's how we smush them together. Here's our point x, here's our point z. Here's our hybrid point. It takes components, z components, if j is in U, and it takes x components otherwise. Okay, so z, the set U is 1, 3, 7, and 8. So we'll take z1, z3, z7, z8. And then what do we do? Everybody else comes from x. So x2, x4, 5, 6, and x9. So it's a hybrid point. And now what we can do is we can see what happens to f of this hybrid point. How different is that from where we started? And if that's really different, then it means ZU has moved the needle. That collection of variables has changed things. So that is the way most of the uncertainty quantification literature works with hybrid points. You pick some things, you freeze some things. So you freeze these guys, pick fresh for these ones, and see what happens. And this can be awkward. Suppose x1 and x2 are highly correlated. Well, you could get in trouble if you change one of them but not the other. You could land in an unlikely zone. So if there's correlated or structured, it could be pretty bad. Here's a famous data set, the Boston housing data. So it has 506 regions in Boston and 13 different predictors. And they were trying to figure out whether pollution changed the value of housing. Here's one pair of those variables. On this axis, what fraction of the lots are large lots by some definition? It can go from 0 to 100%. And this is the local crime rate, which can go from 0 to quite high. And what we notice is there's nobody in here. You can have a large lot, you can have a high fraction of large lots or a high crime rate, but you don't get both. Now, if we start putting together mixing and matching points, we're going to get points in here. They're seriously out of distribution. And whatever those points are, they're not Boston in the 1970s. Now imagine that you evaluate your function f at those points. It doesn't matter if it's a neural network, or just a linear regression. These points don't describe Boston. They're not points that we should be using. Okay, so they're out of distribution. I mean, maybe this one's not out of distribution, but how would you draw the line between what's in distribution, what's out of distribution? That would be in process with error. And so also the model won't be that regularized. Whatever prediction it's making out here, it never had any data like that to predict with. So it's probably not a good prediction. Leo Breiman proposed a method of measuring importance in his random forests. So what you do is you take one of your variables and you just scramble them at random and recompute F and see if anything changes. So if our old x's, say I've got two components, x1, xi1 and xi2, in the new case, well, we'll keep the first variable, but we'll do the second variable in random order. So the first one what used to be the first one goes here, then second, third, fourth, and fifth. So you scramble one, leave the rest fixed. And that's going to be pretty problematic for dependent inputs. And Hooker and Mensch actually have a paper, the first part of the title is Please Stop Permuting Features. So this could cause you some kind of trouble. You could end up with somebody's birth date happening after they graduated from high school. You can give somebody a systolic blood pressure lower than the diastolic. You know, they're 110 over 120. A model will make a prediction there. You don't want that. So we feel like you can't really trust something that uses those. And it's pretty hard to know computationally what's possible and what's impossible. You can even get things that are logically impossible. So the patient's minimum blood oxygen turned out to be higher than their average blood oxygen. Well, if you scramble min and keep the average fixed, that's going to be a problem. Or their min might be different from their max, but they were only measured once. Okay, so you can get things like that. And these are the ones that we could identify ahead of time. But of course, in practice, there would be surprises too. Well, there are two approaches to handling this problem. There's Sobel indices from Ilya M. Sobel, and then the Shapley value from Shapley's famous American economist, from the mathematical economist. Sobel indices really handle interactions. Okay, so they take care of that beautifully, but they have a severe trouble when you have dependence. Shapley can handle interactions and dependence, but at potentially high cost. The global sensitivity analysis literature, it's mostly Sobel. It's been going through since the 1990s. The kind of applications they look at are, you have a function that tells you how your semiconductor is going to behave when you manufacture it, or tell you how the wing of your airplane will behave before you actually make it, or use it on a climate model. So it's a lot of applied math models where products are designed in software before you ever do a physical experiment. Okay, so that's one area that's been looking at variable importance a lot. They mostly land on Sobel indices. Shapley value, it can handle interaction and dependence. And there's a lot of work on Shapley value. I'll mention a few. So locally, Gorbani and Zoe have been looking at Shapley value to say which data points are important. So instead of changing a variable, transpose your matrix and maybe knock out an observation or two. There's, SHAP is an important contribution in this area. There's, we'll make reference to Najmi and Sundararajan. They like a baseline Shapley method and they survey other uses. Back in the uncertainty quantification world, I have a paper there, there's a few others. There's also a paper by Kumar et al. On qualms about Shapley. So they think you can actually get into trouble using Shapley value. Okay, so it comes from economics. And the question posed was, how do you fairly share a reward among multiple causes or team makers? And Shapley solved this in 1953. And here's an example. Suppose we have a team of people in A, B, and C, and together they create $15 million of value. How much does A deserve? Same for B and C. And then Shapley in his math, he assumed something you probably wouldn't know. You know that acting alone, A would have created $4 million of value. Acting together, A and C would have created $10 million. Shapley will assume that you know all 2 to the D output values. In this world, if there had been nobody on the case, it would have been no money at all. Okay, so if you have all of these counterfactuals, so this is what actually happened, but you have 2 to the D minus 1 counterfactuals, how should we split it? And Shapley will tell you, A gets 4.5 million, B gets 5, and C gets 5.5. Okay, so Shapley knows. So how does that happen? Well, acting alone, they're all the same. The differences are coming in here when you get pairs. So what's the logical basis for that decision? And there are competing logical bases, but this is the one people like to use. And so Shapley supposes that you have a team, which is a subset of your D participants. And that subset creates this value. And then the total value is the value where U equals this index set of all D. And then Shapley's going to say that, well, player J deserves phi J, the Shapley value. Now to set this up, we look at the incremental value of putting person J on a team that didn't have person J in it. So this is the incremental value of person J joining the team U. And it's the value of the set U union J minus what you had before person J joined the team. Okay, so this is what we had. You put person J on the team and you get this incremental value. Then Shapley has 4 axioms. The first one is you have to allocate the whole part. You can't like keep some of it for yourself or throw in a bonus or do something else. It has to be completely shared among the D players. Then there's a dummy axiom. If somebody's incremental value is always 0, then they get 0. That seems pretty hard to argue with. And this one also is pretty hard to argue with. Then there's a symmetry. Suppose there's 2 players, maybe it's you and your sibling. And no matter what team we add you to, the incremental value is the same as if we would have added your sibling instead, and neither of you were in the team to begin with. Well, if you always have the same incremental value, then you should get the same share. So those are the first 3 Shapley axioms. The last one is additivity. If you think you know how to handle 2 different games, and then your new game has the payoffs equal to the sum of the old games, then the Shapley value should be additive. We're actually going to use that. We're going to use that one a lot. Some people don't like that axiom. Okay, given these 4 axioms, there's one way to solve it. And even better, there's only one way to solve it. Person J gets a linear combination of the incremental values that they bring to the different teams that you could put them on. And this is a sum over all the subsets that didn't have person J in it. And this is an average over all the cardinalities of those subsets. This formula is a little bit unintuitive. There's an intuitive way to do it. You could build a team from nobody up to everybody in some random order. And then keep an eye out for when person J joins. The split second they join, the incremental value change, they bring some incremental value. You can average their incremental value over all of the d factorial orderings, and you will get this expression. Okay, so that's Shapley value. It's very nice that these axioms, at least the first 3 seem compelling. The 4th one is debatable, and then you get one solution. So he's one axiom short of an impossibility result like Kenneth Arrow got. Okay, so for variable importance, in the uncertainty quantification literature, they usually look at how much variance did you explain? And so you could say the value of that set is how much variance you can explain using those variables. And this has a bit of a history. Somebody used it for R squared. I found out that Sobel indices, one of them is below the Shapley value, one of them is above the Shapley value. And Sobel indices are easy to compute. And so you can bracket Shapley. And this also helps in the uncertainty quantification world. Sobel indices can't really handle dependence, but this formulation can help you handle dependence for Shapley value. But this variance explained as a global thing. It's like all the data, whole distribution. But like, why didn't my uncle get that loan? That's one person. Or why did they send my friend to the intensive care unit? Maybe I don't want to know about all the millions of decisions that were made. Why was that one person given such an outcome? And so we have a target subject T. And then for some T in that set, we actually want to explain what happened to that person. And it's not necessarily causality. This algorithm might have not used a causal variable. Maybe somebody didn't get the loan because they typed their application in all caps, or they used Android instead of an iPhone, and that was enough. That's probably not a real causal thing. But if we want to know why the algorithm did something, then we have to know, what variables had to be important, whether or not they're truly causal in the future. Najmi and Sundar Arajan really like what they call baseline Shapley. So here's this target subject T, and here's what they got, f of xt. And then they select a baseline point. Okay, this could be some default point. Maybe it could be default operating condition. It could be an average of all the features. A little tough if it's a one-hot encoded categorical variable, but you could still do it. And then they try to explain the difference between these, between what that person got and what the baseline was. So what's the value that they pick? Well, it's going to be a hybrid point. We'll change this subset of predictors and we'll keep the old values where they were at the baseline. And then that's the value for the set U. Or you can average over, instead of picking a baseline, you could say everybody gets to be the baseline once and we average. And there's also conditional expectation Shapley, where we just take the expected value of f of x given that subset of variables. Okay, once you've chosen this, that, or the other, it's over. You chose the game, Shapley gives you the answer. The cost is exponential in D. We've been using Monte Carlo when D is large. Some people like that, some people don't. Okay, so then I think the real problem is, well, what should be your definition? Because once you've got it, Shapley does the rest. And here are a few of the papers we have. Here are the papers we have on it. The method I'll show you today is Cohort Shapley in this paper. We'll talk about algorithmic fairness in that one. And another one is for uniqueness. How many people are just like you? If we take log 2 of how many people are just like you in those variables, that can explore which variables identify you. Okay, so Cohort Shapley, we're almost religious about not using impossible combinations. So we're going to use only actually observed combinations. If you use impossible combinations, there's a potential of some adversarial attacks. Okay, so we'll have a target person, T, and here's their vector. And then we say, is person I similar to person T for variable J? So if they're similar, that's a 1. If they're not similar, that's a 0. And then we have to define similarity. For a binary or categorical variable, you would normally just say if the two things are equal, then they're similar. For scalars, you can't quite use equality. You could stratify to 3, 5, or 6 levels, or maybe you could say, are they within some relative distance? Okay, so we do have to define what's similar. Now what we do is we form cohorts. So here's a toy example where there are 5 subjects, and the target subject is person 5. And we have their favorite color. It could be red or blue in this case. We have what they had for breakfast that day, eggs or cereal, a lot of eggs. Okay, this is high protein sample of people. Okay, so ZI1 is whether the person is similar to the target subject on variable 1. Well, red is not similar to blue, so that's a 0, a 0. This one's 1 because they have the same favorite color, then a 0, and then a 1. Of course, the target matches himself. Then we look at their breakfast variable. Subject 1 matched, 2 and 3 didn't match. They had cereal, 4 and 5 matched. Then we look at, did you match on both of them? And then the only match is the original subject. And of course, this row will always be a row of 1s. And then we look at the cohort. So here's a grand cohort that's got everybody. If you only keep the people with the same same favorite color, you shrink to the cohort of person 3 and person 5. If instead you shrink by their breakfast, you get this cohort of subjects 1, 4, and 5. And if you shrink on both, in this case, you only get the target subject. And if there are a lot of variables, it'll be pretty common that you only get the target subject in that final cohort. Okay, so those are the cohorts. And we can look at the cohorts again. So here are those same cohorts. Here's the cohort of everybody. Here's a cohort where you match everything. And then we can think of 2 to the d graph of similarity constraints. So we can start off with no constraints whatsoever. If we constrain the favorite color, then we have this set of variables. If we constrain the food, we get that set of variables. And if we constrain both, we get this. Okay, so this set of constraints gives you that cohort. And now here's our value function. The cohorts are the set of everybody that's similar to the target. And they have to be similar to the target for every feature in the set U. Okay, so that's who matches the target on the set U. And then the value is going to be the average in that cohort. We've also looked at taking the median in that cohort, later the cardinality of the cohort, but most of the time we just take the average of that cohort. And then we think of cohort refinement. We can start with a set of everybody. And every time we throw a new variable into the set U, the cohort shrinks closer and closer and closer to being the target only. And then an important variable is whatever moves the cohort mean the most towards the target. And then once you've set up your value, Shapley does the rest for you. Okay, so our usual value function, I told you that it was the cohort mean. It could also be the cohort mean minus the grand mean, because when you take incremental differences, this will cancel out. So when you center something, it doesn't change the Shapley value. So this is a fourth kind of importance. We start from some blank slate tabula rasa. We don't know anything about the person, and we reveal variables in one order. And whatever variable you reveal, if it moves the mean, then it's important because the knowledge of that variable is telling you something about the prediction for that person. So it's really about, does knowing the value of that feature tell you something about the person? It's nested sigma fields. Here's an example from, I guess, a widely used data set, Titanic. We looked at, say, suppose you predicted who would survive by logistic regression. And for continuous variables, we said if you're within 10% of the range, then you're similar. And here we sort everybody from least likely to survive to most likely to survive according to our not quite black box logistic regression. And then here is their survival probability. It goes from minus 0.4 to 0.6 because instead of 0 to 1, because we just shifted it down by the average. Okay, and then this dark purple line is their prediction, and it's a sum of positive and negative effects for each of the variables. Okay, so the reason these pop up above is there's some negatives down below. And we see this big patch of blue. And one of the variables in the data set was labeled sex, so it's men or women, it's the gender of the passenger. And there's a cluster of people for whom their level of that variable made them more likely to survive. And here's a cluster of people where their level of that variable made them less likely to survive. And not too surprisingly, these are mostly women, these are mostly men. And then another important variable here is the class. Were they first class or steerage or whatever. And for some people, the class helped them, and for others, they didn't. Now, your visual impression here is like how much blue there is and how much yellow there is. And your visual impression is you would sum the absolute values of these things, but that doesn't really correspond to a game or value function for a game. We wanted a way to aggregate from local to global decisions. So what we did, we took a quadratic thing. So this is a quadratic importance for one target. And when you aggregate over subjects, you get variance explained. And so these were by far the most important variables. What if a variable isn't in the model? So, we didn't discriminate against age because age wasn't one of our variables, but we also know that Jones has been a COBOL programmer for 30 years, and we use that. So we have a function that doesn't use x2, but x2 is really close to x1. So baseline Shapley is going to put all the importance on x1. If they're redlining on x2, you can't catch that with baseline Shapley. Cohort Shapley is going to share them. Okay, that's maybe a problem because it would split the importance in two. And there's a nasty trade-off, and there's a catch-22 in choosing how to handle something that wasn't in your model. And Kumar et al. Write about it. But Cohort Shapley can find redlining. And that brings us to the COMPAS data. You've probably seen other talks on it. It's a black box algorithm to predict who is going to reoffend. And the algorithm is proprietary from North Point, and ProPublica took a look at how it predicted for people in Broward County. And they wanted to know whether it was unfair to Black people. And so the way we analyze this data is we look at the subjects who are either Black or white. That wasn't quite everybody, but we're following the way other people analyze this data. And there are 5 predictors: the age, race, gender, how many prior offenses, was it a felony or a misdemeanor, and we're going to follow how Kolakova discretized these things. And then the response is, did they reoffend? Did they really reoffend? And the other one is, were they predicted to reoffend? And so we'll get Cohort Shapley values for those. Now, the COMPAS algorithm actually didn't use race, but the ProPublica people recorded it. The North Point algorithm is proprietary. We can't get f of x. We can't evaluate it at a new point. So no using hybrid points. We didn't want to use them, but we couldn't anyway because it's a proprietary function we don't have. Another ingredient is this algorithm was not trained on Broward County. It was trained on another data set. We can still run Cohort Shapley. So we have our analysis. We're not going to claim that it's a definitive fairness analysis. I think a lot of other people would have input to that. Okay, so here is a histogram of the Shapley effects, the Cohort Shapley effects for the race of the subject. Now, this is whether they're predicted to reoffend. So reoffending goes from 0 all the way out to 1 if they're predicted. 1 is that they're predicted to actually reoffend, 0 is that they're predicted to not reoffend. And we can get the Shapley values, the Cohort Shapley values. And I have a histogram of them here. Every individual has a variable importance. And so if we look at it, these are the importances of race for the Black subjects. Race was not used in the algorithm. These are the importances for the white subjects. And so in this instance, if you tell somebody that the subject was Black, in every single case, it made it more likely that they were predicted to reoffend, and the opposite for the white. Okay, so that's what you get at the individual level. And here they are again. This is that y hat. And here's, did they actually reoffend? So the distributions are quite a bit closer and they actually overlap. The fact that these can overlap means it's actually more significant that those don't overlap. They could have been potentially overlapped in the data they didn't. And here's the residual. Did somebody actually reoffend minus were they predicted? And we're using the additivity of Shapley because if you have Shapley for y and Shapley for minus y hat, you add those and you get the residual. And then here we have something for whether it was a false positive. False positive is you didn't reoffend, but it predicted that you would. And it's less favorable for the Black people. The false negatives are more favorable for the white people. There's actually a lengthy debate, I won't have time to talk about it, as to whether this kind of analysis is more salient than the false positive and false negative analysis. And essentially, if you can calibrate this one correctly, you're going to be wrong here and vice versa. It's just arithmetic. You can't do anything about it. Now we split by gender. So here, this again is the people, this is a histogram of the Black subjects. In orange, it's the women. In blue, it's the men. So the women, the effect was stronger for men than women. And likewise for the white people, the effect was stronger for men than it was for women. Okay, so we can disaggregate, we can aggregate. Are those things statistically significant? Well, we can bootstrap. Okay, so here we have the impact, which is y minus y hat. And here we have it for white people. They were 0.05 on average, about 0.05 more likely to reoffend than the algorithm said. Well, and then the Black people were actually less likely to reoffend than the algorithm said. If you just look at male, it's kind of spot on, and the same for female. Just very small differences. But this is averaging, something adverse for one race with something less unadverse for the other race. And then we can disaggregate to say, here we have the impact for white female subjects. And here's for Black male subjects. And then what are these bar charts? They're from a Bayesian bootstrap. And we like the Bayesian bootstrap here. What the Bayesian bootstrap will do, instead of kicking somebody in or out of the data set, it just upweights them and downweights them by an exponential random variable. And we like that because nobody's ever kicked out of the data. So again, go back to your specific subject. You can look at what happens in a bootstrap for that one person because they never get a zero weight. They're never kicked out of the data. They're upweighted or downweighted. So you could find the person that did the worst by this measure and look at a bootstrap just for them or a subset of people like we have here. Okay, so that is the fairness angle. I'll briefly mention uniqueness. There's this interesting observation by Goal in 2006 about how 87% of the US population could be uniquely identified by gender, zip code, and birth date. So then it's kind of interesting, what variable identifies you the most? And we'll take minus log 2 of the number of people in your cohort. If that's the value function, then a big phi j means it can really identify you better. And so we can look at, it's, like from privacy purposes, what variable would you want to hide? Or if you want to, if you're on the other side, what variable do you want to know? And we looked at some voter data from registration data from North Carolina. It was over 7.5 million people. We got about a 2,000-fold speed up using a data structure from Andrew Moore and Lee, an all dimension tree. And then we can see how identifying is your party affiliation in this zip code, or how identifying is your age if you're in that age cohort. So we can do individuals and aggregates. Well, there's actually a lot more to say about, especially the Broward County thing, like what response is the most appropriate one to look at? What variables belong in the model? If you have a missing variable, just like causal inference, how do you probably can't handle that if there's an important variable that's missing. Even if you have a variable, which one should you include or exclude? Like in an experiment, you don't adjust for something that happened after your randomization. In the North Pointer setting, some people would say, well, the number of priors that a subject had, that's already somewhat racially tinged. So should you count it or should you not count it? What subset of subjects should you use? So those are sort of next things to think about. Also, the Shapley goes beyond just one at a time. You can get a Shapley effect for things acting in pairs. Okay, So that's the talk. I have many people to thank. I have my co-authors, Masayoshi Mase and Benjamin Seiler. I'm deeply indebted to Masayoshi for bringing me this set of ideas and problems to work on. It's been very fruitful and I've quite enjoyed it. We owe something to Chiara Sabati. Masayoshi took her literature course on algorithmic fairness. We have funders, and I want to thank HAI for being such a such good hosts, and especially Casey, Vanessa, and Deep. And thank you all for listening.
All right, thank you, Art. We do have a few questions in Slido, so I thought we can start with those. So first, the first question I want to highlight is, it seems like some of this work relies on background intuition about what we want from the explanation or what we want from the results. What does that explanation look like? And are there formal criteria for evaluating those explanations?
So I kind of like human in the loop here. So I would feel like if I was talking to, I don't know, defense attorneys or prosecutors or somebody, they would say something about the Broward County data. And then if I was using it in another context like medicine, I'm not sure that a set of axioms that works for the fairness people would be the right thing to use in the intensive care unit. I think I'd want to be deferential to like other scientific backgrounds, and I'd be very hesitant to push one solution. Even in one analysis, I might actually want to look at two different solutions and then weigh them and say which one is better.
So just kind of like following up to that, based on kind of the industry you're implementing this methodology, you would want to adjust kind of how you're using the algorithm and some of your constraints. Is that true?
Yeah, I think it's really dangerous to hand off like a black box solution that somebody just downloads and pushes their data through without having somebody think it over. Like there were a lot of very searching questions about, like, well, for instance, we grouped the number of prior offenses the same way that Cholda-Kova did. What's the right way to group the number of priors? That's actually a hard problem for us. And I think those sort of problems bedevil any variable importance method. But we would want those to be slightly in the hands of the domain experts, or at least in consultation with the domain experts.
Okay. And then can you speak a little bit about what the advantage of this approach is over the conditional Shapley methodology?
Well, I think we're pretty much in the conditional Shapley land. There is a slight difference. We can define similarity in ways that won't exactly be conditional Shapley. But if we define similarity by equality, then we're doing a kind of conditional Shapley. Now, where we differ from Najmi and Sundarajaran is we like conditional and they don't like it. They don't like that a variable that's not in the model could get some importance. We like that a variable that's not in the model can get some importance. And the domain experts might differ. The one way to, the SHAP approach also uses something like a conditional expectation, but they start augmenting with other data points, or at least that's what was in, there's a paper where people adversarially tweak out of distribution data, and they can make an unfair algorithm look fair by tweaking it in places where you never even had data. So we avoid that, but we're kind of in that same cluster of methods.
Yeah. So you mentioned something interesting, that this methodology can attribute importance to a variable that's not actually there,
Yes.
Which create, it's a bit controversial, but very important in the context of algorithmic fairness. Right. Can you talk a little bit more about how you're thinking about this and how you would approach this.
Well, I feel like if you can't detect importance of a variable that's not in the model, then you just gave up on catching redlining. Okay, so you just gave up. Like somebody could find some proxies that strongly predict the protected variable and use those, not use the protected variable, and pretend to be fair when they're not, or maybe they don't even know. And so I feel like it's a catch-22. I feel like you have to be able to do that. Now suppose you put in 3 variables that are close to the protected one. The Shapley thing will share the importance among them and dilute them. Somebody could gerrymander it and dilute it down to where, the protected variable doesn't get over the threshold. And I feel like you need a human watching that. Like, let's be human-centered about this part of the problem. And yeah, and probably more than one human in some of these high stakes things. I think it's going to take multiple humans.
Yeah, that's good. Yes, we're very pro human-centered
Okay.
over here at HAI. So let's see. So there's one question in here about scaling to a large number of input features. So it seems like the more features, the more likely you are to have cohorts with a single member, which I think you mentioned in your talk. How can you speak a little bit more about that?
We thought actually quite a lot about that. So if there's a lot of features, there's a computational problem. If there's a lot of features, then the cohort comes down to the individual. If it's just one person's data, that could be a noisy number. If it's the output of a well-trained and regularized machine predicting for that one person, even though there's n of 1 in the cohort, that prediction might be based on n of 1,000,000. So it could still actually be a meaningful quantity. So we don't worry about that. Then what I didn't show is we found some interesting things. If you look at the incremental value for adding j, when there's like 3 prior variables, 10 prior variables, 20 prior variables, it almost looks like it has the same distribution in a lot of data. And we're going to try to exploit that to look at better algorithms.
Okay. Yeah, so there's another question kind of related, and is there, or do you have a sense of an upper bound on number of variables that can be? Or
Well, we're pretty excited about trying something with, say 500,000 variables, and then you'd have to make a compromise. You're not going to do d factorial or 2 to the d in that case. And so then there has to be tricks and strategies and approximations. So then we would not be able to actually compute the exact thing, but we might be able to get an approximation. Sometimes you're lucky that like most of the variables don't matter whatsoever. It's sparse, and a few of them matter, and maybe they don't interact that much. So if there's an enormous number of variables, then you have to depend on luck, and you can assume the luck in your theory, and then you have to test it in your practice.
So we are almost at time. I'll just ask one last question. At the end of your talk, you talked about like some additional things to think about, for example, subsetting the data, and some other aspects, including variables. Is there a particular way you're thinking about how to determine what to include or exclude, for example, when subsetting?
We haven't really thought about that. So in all of our examples, we just take all the variables that there are. And maybe you could have a diagnostic that warns you if 2 variables are close proxies, then they're going to share their Shapley value, and you're at some risk. If 12 variables jointly are close proxies, that's going to be hard to even find. But I think we would just think about what the variables mean in a small enough data set. if there's enough variables, you can kind of think about what they mean. And that would be what we would
Yes,
start with.
probably including kind of the domain experts.
Yeah, so we're being pretty retail here. We're just,
Okay, great. Yeah, so we are at time. Thank you so much for joining us, and thank you to our audience for joining and asking questions. We really appreciate it and are happy to have you here. The topic for next week is a blueprint for a national research cloud presented by Stanford Professor of Law and Political Science, Dan Ho, and HAI Privacy and Data Policy Fellow, Jennifer King. So all of you in our audience, remember to register for that, and we hope to see you there next week. And thank you again to Art and his team for this wonderful talk.
well, thank you, Vanessa, and thanks to everybody who came.
Thank you.